we'll just get set up. So yeah, thank you so much, everybody, for joining. I am excited to talk to you today about kind of Q# and how I've ended up using it for a recent research project that I've been working on. And if you want to follow along, all of the slides here, which are actually a Jupyter notebook, you can find all of them at this bit.ly link. I have put that also in the meeting chat if you want to look that up later. So, and I'll also point out that some of this work has been supported by the Unitary Fund, which is a nonprofit that gives out micro grants for open source quantum software. So with that, yeah, as Mark said earlier, I do a lot of random stuff right now. Everything from writing textbooks. So Learn Quantum Computing with Python and Q# will be out here shortly. In print, it's already out in ebook version. But yeah, I also do a lot of streaming on Twitch. And so I like making these fancy transitions and whatnot. But basically the point here is to help show people that quantum computing isn't as complicated as they might think, and that we have a lot of really cool software tools that we can get started using right now. But also relevant for this talk here is I'm also a researcher. So I did my PhD in quantum computing at the University of Waterloo, working on building hardware for quantum key distribution satellites. So basically doing quantum communication to space. And so yeah, I have a background in more hardware research and have recently kind of pivoted more to doing software research side of things for quantum. So today, I want to start by introducing you to a research project that I've been working on, give you a tour of Q# and kind of help motivate why we're using it for our research, show you actually what the library looks like. So you can see, like, here's case study actually using it. And share some tools and resources that I found helpful that you can leverage if you want to use Q# yourself, whether it's for hobbyist reasons, research, whatever you might want to use it for. Cool. So what is the actual research problem we were looking at for this project? So you've probably heard of memory before, or random access memory for your computers. You all have some on whatever device you're viewing this presentation on right now. And the nice thing is classical RAM is really cheap, fast, colorful in some cases. And yeah, so it's very easy to get. And it's generally laid out as an array of cells that you can read to and read from and write to. So the question is, do we need something analogous for quantum computers? And the answer is possibly. They serve a good way to transfer classical data to a quantum computer, like basically as an I/O interface, you can kind of think of it. And some quantum algorithms that we know right now, especially with those in quantum machine learning, already kind of assume that we have access, that they'll be given a black box that is this memory, and that basically use of it is free. And the other part is there's there are more ways we can actually read out from a memory on a quantum device than we could on a classical device. Like if we read out memory from a classical device, oh, I see, the screen is shared large. Yeah, it's just my webcam. So if you can like maximize or pin me, I think that's probably the best way to do it there. Okay, cool. So yeah, there's lots of different ways you can actually read out a memory from a quantum system. You could read out the data into a phase, you could read out the data into an actual register of qubits, or you could read out the data as a complex vector as a part of like a larger register state or something like that. So there's a lot more options, which means there's kind of a little bit more complexity than just like bits in, bits out. So if we continue here, the big problem, as I kind of alluded to earlier, is that it's actually not even clear if we can do this at all. Like not even fault tolerantly, just can we even do this at all? And the challenge becomes that the resource overhead to query and read and write information to and from these, from a QRAM, however we implement that, the resource costs of that basically outweigh any speed up we get from the actual quantum algorithm itself. So that can be, that's a little depressing. That's obviously, we have plenty of other quantum algorithms that don't necessarily need quantum memory. But it's something that I think is a really interesting open question for us to really help characterize and figure out, you know, is this a resource we can kind of rely on and write algorithms towards? So that's kind of the algorithmic level problem. There's also other things like physical limitations of coherence time of your qubits, error rates, and that kind of contribute to what makes implementing QRAM hard. But we definitely have, there have been a lot of interesting proposals for this though. So there's tons of papers that talk about different, basically different architectures for what a memory for a quantum computer might look like. And so it's kind of taking a look at some of those resources and thinking about this problem that kind of spawned this project. And I'll also note, if you want to go in as a deep dive on like the technical scaling limitations or other algorithmic questions about QRAM, my collaborator on this library did a talk for University of Technology, Sydney. I'll put this link here in the chat real quick, in case you want to check that out. So she's a theorist who works on QRAMs and goes into a lot more of the quantum theory details if you're interested. But my goal here as an experimentalist who I feel like I'm practical about things, and I want to actually figure out like what's a path forward. So, you know, seeing all these different proposals, knowing what the problems are, how can we actually figure out what to do here? And I think the main outcome we had was like, all right, well, we have all of these papers with proposals. Can we actually just implement them and try them out? Like, obviously there's limitations if we want to run on hardware, but there's simulators. So they're, you know, taking the kind of skills that our team had, and usually my general approach to most problems, which is, can I get a computer to solve it for me? You know, I took a look at so this is the Quantum Open Source Foundation website, again, here in the chat. But they have a huge list of basically every project package that is open source for quantum computing. And you can look through and see there's tons and tons of different options. So it's like, from this huge list, how do we actually pick what to use for this project? Because there are options. So our criteria were basically, we want to implement algorithms. Because we're in, like, one of the biggest challenges with QRAM here is at an algorithmic level, not even specifically to a particular like error correction protocol or to a specific hardware. Like, is it even possible at all? Like, can we get the scalings to work out such that we still get a benefit from the algorithm while having QRAM as a part of it? So we really wanted to kind of implement at that higher level and be able to talk about the algorithm there as opposed to any sort of specific version of the algorithm on a particular hardware device. And we also wanted to make sure that these were tools that helped enable research. So being an open source project, and we wanted to make sure that actually other people could use this result and actually build on it and learn new stuff. So, and we also really wanted to work in a community where we felt like we were included and a part of it. So that kind of were the criteria that drove our decision. So spoiler alert, we picked Q#. So now I'm going to transition to showing you actually what Q# kind of looks like and why it really worked for us given the problem that we had. So, but first, I wanted to actually, this is my one Ask the Audience question. Does anybody, what do you know about Q#? I find this as an interesting icebreaker question. Nothing. Yeah, I find that's the case quite frequently. C# but with the Q. Yep, that is true. Not much yet. Cool. Yeah, so I think that's kind of a common not problem per se, but just there isn't a lot of visibility for this, I think, with the either research or hobbyist community at the moment. But so let me just do a definition sort of thing. Q# is a Microsoft's quantum programming language. It's open source. So just like pretty much all the other quantum software tools, they're all open source. And Q# is a new domain-specific language. So it's not a Python package. It's an entirely new, looking to be up to speed by the end of the election. Yeah, we'll be stuck in our houses for a little bit longer here. So yeah, Q# is a new language. It comes with a development kit as well, so that includes, your compilers, your editor, extensions, everything to kind of make working with Q# feel like you're writing Python or feel like you're writing C# or whatever your language of choice is. It is it has nothing actually to do with C# other than Microsoft is really bad at naming things. So it's an entirely new language. It does not share anything in common with the flavor of the language. Feels kind of like a mix to me of like Python, a little bit of Haskell, and maybe a little bit of .NET stuff, but like mostly, or just maybe more generic object-oriented stuff. But really, it's much more functional, like a functional language. And it's designed to be integrated with a number of different languages and platforms. So honestly, I spend most of my time using Q# from Python, given that I am primarily a Python developer. So what does it look like when you're actually going to run a Q# program? So your Q# program would be here on your left. You've written, as a part of a program, a bunch of operations and functions. You can pull in a bunch of libraries, which is one of the things that really helps speed up our implementation of the QRAM stuff. So basically, we have contributed a new library that you can pull from for other programs. And so that's basically the entirety of your program. And then you have a host program, which this is technically optional, but the idea would be like you'd have maybe Python running, where you have Python generating the data to go into our memories and plotting resource counts and stuff afterwards. This kind of really meshes with, I think, the general model for quantum computing more generally of it being an accelerator. So it's a hardware accelerator, just like a GPU is a hardware accelerator. So the idea is that your GPU doesn't usually have its own program per se. You call, as a part of another program, you like call out to it, it does some things faster and gives you some results back. And so that's the idea here, is basically Q# is governing the acceleration of what's running on your quantum computer. And so in Q#, there's also this, it also very strongly decouples the idea of your program and where you're running it. So it has this concept of a target machine, which you just specify basically as part of a project config. And so you can target anything from simulators. There's a number that come out of the box with the quantum development kit. You can write your own simulators as well. I've actually done that. It's pretty fun. There's resource estimation as well. And you can also target hardware. I actually got to do this on Azure Quantum just last week for Microsoft Ignite. If you want, you can sign up for the private preview. So Azure Quantum and the hardware access is currently in private preview, but and should be going public soon. That's all I know. But yes, I'm just pulling up the link for become an early adopter. Here we go. So yeah, that's the link to sign up to the private preview if you're interested. So yeah, this is basically what it's going to look like. We're going to write a program, we're going to pick a target machine, and we're going to let a host program, or just the command line, actually handle kind of shuffling between the three. So as you can see, as you saw from that diagram, there's basically two things you're writing in Q#. You're writing functions and you're writing operations. Functions are kind of like like mathematical functions, as in things that are like deterministic, classical, like maybe reversing an array or calculating sine or a log, something like that. Operations basically are everything else. And in particular, if you're working with qubits, operations on qubits are viewed as side effects in Q#. So that basically that has to be an operation. So let's actually take a look at what code in Q# looks like. So I'm going to do the standard like hello world thing that everybody does for new programming languages. So I'm going to define a function because there's nothing quantum, there's no side effects about this. I'm just printing a string. And you can kind of see this is why the title of the talk had message wrapped around it. So that's basically your print statement. And I can then simulate that. So I'm currently running code in a Jupyter notebook. And so the way I pick the target machine here is basically by this magic command. So I'm choosing basically the built-in simulator to run all the code here. So great, we've got the kind of like basic hello world working. Let's move forward and actually take a look, what does it look like to use qubits? So as I mentioned before, qubits are a resource that you request from the runtime when you need them, and you return them when you're done. So I'm going to start by opening one of those libraries, actually, the measurement library, because that gives us some nice additional options here. And then I'm going to define this operation called QRNG. So this is a very basic, basically we're going to prepare a qubit. I'm going to put it in superposition by applying the H operation here. And then I'm going to measure and reset the qubit, and I'll be measuring it on the z-axis here. So there are tons of different like convenient kind of workflows that come from the libraries. This happens to be one where it's just like, yep, I've got a qubit, measure on the x-axis, reset it when we're done. So great, I've got that defined. So if I move on here, again, let's simulate that. So I can simulate the QRNG and I can run it a bunch of times and it should basically be 50-50, 0 and 1. Obviously not the most interesting algorithm, but it's a good kind of base case to show what it looks like to work with qubits. Now, let's get to some more complicated operations here. In Q# we have the functors, which I know is a funny word, but that's what they're called, adjoint and controlled. And basically what that allows you to do is when you write an operation, you can actually have Q# generate the adjoint, or basically the operation that undoes that operation. Or you can ask Q# to make a controlled version of that operation. Now this is pretty helpful because often I don't, like it's easy to say, all right, so here we're going to just make an operation that applies X. I know that it's very trivial. I don't need to technically define a new operation to do that. But what I want to show here is that if I define that, so X just flips your qubit, then I can make it controlled on a whole register of qubits by literally just adding the controlled functor here and adding another argument for the qubits we're going to control on. So I can define those, and then I can apply multi-controlled. Yeah, so, and here we're actually going to use it. So again, you see we've got the using statement. We're getting 2 registers of qubits this time, one that has 2 qubits, one that's just 1 qubit. I'm going to put the controls in superposition. So basically, yeah, so we'll have the controls on the X in superposition. Then we apply the operation. And then you can see here, I've opened the diagnostics library. So again, this has a lot of good stuff for kind of, you know, as close to like print debugging as we have for quantum systems. I can actually ask whatever target machine is running, hey, tell me everything you know about the computation at this point, please. For the simulator, it'll be able to tell me the state that it's keeping track of things. For hardware, that's not necessarily the case. Hardware might tell me like what temperature things are at, or because we can't directly read out that state vector in real life. So we've got that defined, great. So this is actually, we're using this controlled X or controlled, I guess it'd be a multi-controlled not, yeah. So we're already actually kind of looking at one way we can run Q# programs, but you can run them from the command line as if they're standalone applications. So that's the case where basically you don't worry about the host and you just let the quantum development kit basically stub that out for you. You can run Q# from Python or any .NET language platform or programs. So whether that's C#, F#, whatever you like. I've been trying to figure out how to run it from Unity, the game dev engine. I think because that's basically a variant of C#. So you can actually make it really easy to process data going in or visualize data coming out. Even though you could obviously do all those, you can do those things in Q#, I find a lot easier still to do it in languages, like if you're doing plotting, like to just do it in Python. Yeah. So I've had some game devs come in on my Twitch streams who are like, oh, we should like make a Unity plugin to work with Q#. So if you're interested in that, contact me later on Twitter and we'll talk about it. But the other way, that we're doing literally right here, is running in Jupyter notebooks. So right now the kernel for our Jupyter notebook is, which if you haven't used Jupyter notebooks before, they're basically, I kind of like to think of them as, it's like a visual REPL. Like you can actually, you run individual cells. I mean, as you've been seeing here, I just hit Shift Enter on these. That kind of adds them to the session, and then I can either run that code or modify it again. And I can do that with either a Q# or a Python kernel even, which is, so if I have Python notebooks already made up, it's easy for me to swap out swap them to include Q# as well. So again, we can run this controlled functor, or use controlled functor to basically generate new operations that we don't have to figure out what they are. So I liken this to, like, I didn't have these tools when I was doing grad school. We always had to work out by hand, or try to get a linear algebra package to do the complex conjugate of whatever operations we're doing, and program that in and actually hand code everything. Here, there's a lot of stuff we can actually ask Q# to basically do for us. And I kind of think of that as like, in a programming context, it's like going from trying to manually manage memory to asking a language like C++ and later languages to like, can you manage the memory for me? So yeah, that's kind of the flavor that I get from this. So here you can see what dump machine looks like. And we prepared, so we had 2 control qubits. So that they would have been in a superposition of 0, 0, 0, 1, 1, 0, and 1, 1. And then basically, we should see basically 4 states here, where the first 2 qubits are controls. So there's 0, 0, 0, 1, 1, 0, and 1, 1. And with this last one, we can see then the last bit actually flipped, because then both controls would have been true. So slightly more complicated than just 1 control qubit, but I like that you can, still not too hard to work out what the state should be. So we've been using the simulator target machine a lot here, but that actually isn't the only option we have. So I can list basically all of the different magic commands that are in the Jupyter notebook here, which a lot of them map specifically to different target machines. So I can simulate, I can estimate. You can actually also see here a lot of the infrastructure for Azure Quantum. So that's actually already live. So you can see you can just submit jobs directly from your Jupyter notebooks and stuff like that straight to Azure. So basically your job goes to the cloud, and then the cloud takes care of dispatching the jobs to whatever the hardware, whatever hardware target you want. So this was important to us, though, for the QRAM project, because one of the challenges here is that we can't necessarily run the circuits, or simulate or otherwise, that we need to basically implement these QRAMs. They're too big. And so what we wanted was a way to actually be able to estimate, and like do resource counting, right? Even if we can't run it, let's just count up what it'll take to run it so that we can work things out from there. And so it was really one of the main reasons that really pushed us towards Q# was some really nice built-in resource estimation. So I can, on the same operation that we just simulated before, the use control functor, we can run an estimate on it. We can see here that it will take 3 qubits. Cool. It'll take like 5 kind of, the depth of the circuit is 5. I'll tell you how many T-gates, and this is all also configurable as well within Q#. You can use kind of they have another target machine, which is a trace simulator, where you can really, really fine tune how you want to do resource counting. And one other thing that we did a lot of for this library was unit testing. So in general, good code is unit tested, but it's an interesting question of like, what does that mean for code for a quantum computer? And so here, basically what we did was we used a lot of the built-in library support for Q# to really make this easy. So, firstly, we kind of checked things like with using functions like fact and asserts to basically, which asserts work very similarly to how asserts in Python work. But the idea is basically you can provide checks where if the check doesn't pass, the program fails, or you can basically control what the behavior is at those points. But here, we're just basically allocating a qubit, making sure it's been allocated in the 0 state. So that's what we're doing with this assert here. And we're doing that to every qubit that is allocated in this register. So if we actually go and run this, I have full confidence that the test will pass. We can change however many qubits we want here. The test should pass. So those are kind of like the basic checks, but something that was a little more complicated was we were doing a lot of looking at a bunch of different papers that had different optimizations of like kind of some of the same core like algorithmic steps. And so we wanted to make sure when we were implementing them that A, our implementations were faithful to like what the paper said that they should be. And B, like if we were making a modification and like trying to optimize an implementation, that optimization in fact was still the same result for all inputs. And it turns out you can use a really neat theorem called the Choi-Jamalakowski isomorphism, which we can talk, if you're interested in this, ask me afterwards, I can go through the details with you. But basically what it allows us to do is give Q# 2 operations and say, are these the same for all inputs? So I'm gonna start here by defining an operation that's apply C0. So, it's literally a C0 as control NOT gate, exactly as you'd expect, 1 control qubit, 1 target qubit. So we've got that. There is a circuit identity where you can basically flip the control and target on a C0 by putting H's on either side of the C0 on both the control and target. So here you can see I've defined an operation that's apply C0 the other way. And what I've been able to leverage here is a really neat pattern in Q# called within apply. So these are 2 blocks that if you've worked with quantum algorithms before, you're probably pretty familiar with this pattern where you do some preparation, maybe like prepare your registers, whatnot, get things the way you like. Then you do kind of like the core part of the algorithm. And then you need to undo that preparation to kind of get the answer back to the register or do phase kickback or something like that. So you have this pattern of like prepare, do, and then unprepare. So given that Q# is a language designed for quantum computers, this is a native kind of or an intrinsic part of Q# is to have this control flow called within apply. And basically what that does is I can say here, I want to apply H's to each of the qubits in the register at the beginning. Then I want to apply C0, and then Q# will then apply H's afterwards, basically do whatever is in this within block, but do the adjoint and reverse so that it undoes them, basically. So I find I use these within applies all the time. It is so helpful, because when I didn't, and regardless of what language, when you're trying to make sure you write out kind of I always either mix them up or forget to adjoint something. It's just a good, like, let the compiler take care of that for you. So we can define that, and we can also define, so here's where that Choi-Jamalakowski isomorphism comes in with this assert operations equals reference. So with this, I can say, hey, use 2 qubits, and here are my 2 operations. Can you please prove that these 2 operations are identical in their effect? And so hopefully if I simulate, check that this works, it works. I mean, it's not super interesting from that standpoint, but yeah, this is a really helpful kind of technique that we leverage to make sure as we were iterating on implementations that things were still correct. So, all right, we found a tool that has a couple key features that were really, really useful to us. So our plan now, or then, was to use the functions and operations to implement these the QRAM proposals, leverage the libraries, functors, and other features to reduce how much code we need to write because we were on a limited time grant. 3, set up a bunch of testing features to make sure our implementations are correct and faithful to both the implementations and any optimizations we make are faithful to the original papers, and then hopefully publish, which is where we're at right now and in the process for. So let's actually take a look at what this library take a look at the library. So this is the repo for it. It's all open source. You can always take a look at what's going on. And the basic layout of the actual files and stuff looks like this. So we have docs, we have our samples. We've implemented samples for each of the different types of QRAM that we have, as well as some kind of like algorithmic use cases. So we actually did an implementation of Grover's where you can swap out some of the reflections with calls to the QRAM oracle. And then the source for the library and tests, pretty simple. And yeah, like the source is where we actually have all the implementation code. You can see here, we used VS Code a lot to basically work on both the paper, look at other papers, and actually implement the oracle or the QRAM oracles. I keep calling them oracles because basically, so an oracle in quantum algorithms is basically a way to take a classical function and implement it and wrap it up and use it in a quantum algorithm. And so here, like this is a memory, it's classical data for the most part that we're trying to keep track of. And so we basically need a way of kind of wrapping that. And so it's usually viewed as an oracle. And so currently we have implemented bucket brigade with bit and phase queries for QRAMs and QROMs, which just like the kind of classical distinction between random access memory and read-only memory, QROMs are quantum read-only memories, but those can actually be cheaper to implement if you don't have to basically if you don't have to update the data, you can kind of hard code what you want the data in just a regular circuit. You don't even have to set aside qubits for, you just have to have a circuit that you need to run. And we've implemented a few different versions of that. Yeah, you can see here, one of the other things you can do, so Q# is a strongly typed language, and we leverage that to help us kind of make some new types to help organize the new structures that we needed for the QRAM. So a new object of type QRAM would basically need to have a phase query implementation, a bit query implementation, how to write to it, and then some metadata. So that's kind of like, and you can see the type signatures for each of those, like what types you would need to have to do a write, stuff like that. And that's all nice, but let's actually take a look at using it. So I'm going to start by actually loading our library here. So the library is actually published on NuGet.org. So just like you get any other package for Q#, or really any, Q# does use the same package hosting infrastructure as like C#. So they're all on NuGet.org. I'm going to open a bunch of libraries here just to make things easy. And you can see the last one here is actually opening library, QRAM. And so let's try an example of full end-to-end what it looked like to use a QRAM. So I'm going to start by defining a function that basically hard codes a bunch of memory data. So I'm using some custom types like we defined in our library what a memory bank looks like. But basically what you need to know about this is these are our addresses. So at address 0, 2, 4, and 5, we have the data values 0, 5, 2, 3. Just randomly typed from my brain values. So we've got our data now. Now we need a way to actually query. In this case, I'm going to use a QROM. That's no particular reason other than I like them. As I showed, there's at least 3 different options you have here, but this one happens to be a QROM. And you can see kind of the basic flow here. We're going to query and measure a QROM. And so as input here, we'd need a QROM passed as input, and we'd want to know what address we actually want to look up the data from. So to do that, we're going to use using, so that's how we get qubits. We're going to get a address register and a target register. And we get those with the appropriate sizes here based on the metadata from the memory we've passed in. Then we're going to use some of those great library functions here, apply poly from bit string. So I can actually say, I have this bit string, it has 1s and 0s. I have this qubit array that's the same length, and I would like to, where there's a 1 in my bit string, apply this operation. And in this case, the polyx operation. So that's basically how we're going to make it easy to prepare our address register, as you can see here, with the address that we're trying to look up. So the address here is binary encoded. So we basically have to go from an integer to a binary encoding in a qubit register. We can do that one line. Then literally we just call read on our memory and pass in the address and the target where we wanted to put the answer. Then we can reset the address register and return the answer by basically measuring as an integer our target register, where we basically say how we want to interpret the bit string that we've measured, whether it's little endian or big endian. Great, so that's kind of the core workflow there. And then I need just one more high level wrapper to basically say, here's the data, here's the memory that get passed into that. So we'll do that. And yeah, so as a reminder, this is the data that we actually put in. Those are the tuples, address, and data. And so it looks like if we query address 2, we should get 5. If we query, and then we can literally, without changing anything, immediately see what resources were needed to do that. So here you can see it took 7 qubits, circuit depth was 70, took 105 T-gates, etc. So yeah, this was pretty exciting, an exciting point to get to, because we actually went from just academic papers to an actual implementation where we could put in data, actually have them function. Obviously here, these are for small examples that we can simulate. So I can simulate up to about 32 qubits with the built-in simulator for Q#. That's a full state simulator with no noise. But I can estimate, and like I could put in, you know, probably, okay, that might be too big. I can, oh yeah. I can make this a lot bigger and still actually be able to, I probably have other checks that are going on preventing me from doing that. But the idea is I can actually estimate for much bigger instances, and that will be really, yeah, I can't do anything larger than 3 address bits, I think, for this, just because of what was hard-coded before. So anyway, yeah, so that was basically the setup, and now you kind of know what it looks like to actually implement QROM. We also have in the library a bunch of tests, as I mentioned, because those really help us check both these small instances, and we can verify the resource counts we expect on larger instances by using that estimate. And we also have tried to create good docs for folks to actually be able to use this. So this is something that Olivia has been working a lot on. both in terms of the paper that we want to write here, as well as like user docs to help people actually use this. And what we'd really love to see is folks actually using this as a part of other algorithms, like quantum machine learning algorithms. So yeah, that's kind of part of what's next for this. But yeah, so we want to do more detailed resource counting. So we want to, there are parts where like we don't really care about the resources being used here, and other parts that we're like, yes, this is actually the critical part. So we want to be able to customize that a little bit better and basically improve documentation and get a paper out. So that's pretty much where we're at. And you can see all of this with our milestones publicly on the repo, so you can always see where we're at on this. So lastly, I want to just go over real quickly, how can you actually get started using Q# for your own projects? So probably first, getting more familiar with Q# itself. As with anything, checking out the docs is probably a pretty good idea. So you can find those at docs.microsoft.com/quantum. Shameless self-promotion, I've written a book, so you might find that helpful. And as well, I do a lot of live streaming on Twitch. So I have office hours actually tomorrow. So I do office hours on Tuesdays, do a bunch of quantum development on Wednesdays, and I play games on Fridays. So all at 10 a.m. Pacific. So yeah, come hang out and join us and ask whatever questions you have about quantum computing. I'm always happy to talk about that. So those are some options. The next step might be joining the community, and I highly suggest checking out qsharp.community. So this is basically the community user group for Q#. We work on a lot of projects together, and our mission is basically to make sure everyone feels safe and welcome in our space. We want to make sure that we're communicating in ways that are helpful to our community. So you can check out our Slack at slack.qsharp.community. And we want to make sure we can support members of all skill levels. So this isn't only for researchers or only for hobbyists. We really have a pretty broad range of members. And so there's kind of people you can talk to or work with at all different levels. Yeah, and I'd encourage you to kind of check out like some of the projects that we've been working on and see if there's anything that might be of interest to you. QRAM is obviously one of the Q# community projects, but we actually just last week started working on one where we're going through the quantum, the algorithm zoo, which is kind of like the list of all known quantum algorithms, and just going through and trying to implement them in Q# and see what it looks like. So that's pretty fun. So in review, Q# is a high-level open source programming language for writing quantum algorithms. It's designed specifically for quantum computers. We have used it to actually implement a number of proposals for QRAMs in Q# and are working on kind of a paper based on doing some resource estimation and comparisons of those different proposals. And the Q# community is a pretty great resource for help if you're working on Q# projects or quantum computing projects more generally, or not exclusive. So yeah, so and I see in chat, do I recommend any good books to get started with quantum algorithms and the maths required? That's a good question. Looking back at my bookshelf right now, I think the KLM, what is the full name of that? Nil Mosca Laflamme. Yeah, Neil Laflamme Mosca book, I think, is a pretty good quantum algorithms book, and it also is not super big. So it's, but let me put a link to the quantum algorithm zoo here real quick. So this is maintained by Stephen Jordan, who's a researcher in the field, and it's a really good resource if you're just looking like, what algorithms are out there? They're all listed kind of by category. So yeah, let's see. Which operator does C0 map to? Spin XL. I mean, C0 is a quantum operation itself. It's basically a controlled version of X. So it's a controlled X gate. So I think that's, and then Faisal, how does Q# differ from other options such as Qiskit? Yeah, so I think kind of one of the major differences between these different language options is kind of the level of abstraction that they're targeting. So kind of like you could write in basic or assembly level instructions for a classical computer, which is necessary in some cases and how you get really good optimization. Sometimes you also want to write in Python or a much higher level language where you don't care at all about the hardware and you just want to write kind of conceptually, like I want to write a web service or something like that. So kind of the way I tend to think about it is like Qiskit, which is to kind of like a lower level assembly language that is hardware specific, versus Q#, which is a kind of higher level abstract, higher level abstraction where the focus is on the algorithm part and not so much the hardware that you're implementing it on. That's not to say that you can obviously write algorithms with Qiskit, and you can obviously also write hardware-specific optimizations with Q# as a library or a simulator. There's lots of good options for that. So yeah, I think like personally, one of the reasons I tend to like Q# over Qiskit is just because it feels like I don't have to fight the language to write the algorithms parts that I'm interested in, which makes sense. It's designed to do that. So that's kind of the short version.
Good. Thank you so much, Sarah. Are there any other questions? And thank you especially for all the links that you provided. I'll be sure to include those on the comment when I post the recording link tonight. I'll include these links.
Cool. And you can find all of the links and the source as well in the repo, and you can literally run the same presentation in your browser. So I have that all set up. You don't have to install anything, and you can poke around and use whatever you like.
Good. So okay, thank you again so much, and that was great.
Yeah, thanks for the opportunity.
Thank you, everyone.
Have a good one. Thanks.